Hello and welcome, everyone. Thanks for closing the door. My name is Daniel Russo. I'm an associate professor of software engineering at Aalborg University in Copenhagen. And for today, I have a big pleasure to chair this very interesting session. And I would like to start right ahead, inviting Jinyang from the Chinese University of Hong Kong for his presentation, Incident Aware Duplicate Ticket Aggregation for Cloud Systems.
Okay. Hello, everyone. I'm Jinyang Liu, and I'm happy here to present this paper, Incident Aware Duplicate Ticket Aggregation for Cloud Systems. I'm from the Chinese University of Hong Kong, and this is a joint work with Microsoft, the Chinese University of Hong Kong Shenzhen, and Chongqing University. Nowadays, many applications have migrated to the cloud, like Office and Meta and so on. And the cloud systems have been larger and larger with a very large scale, like Microsoft Azure now has more than 50 regions across more than 140 countries, and more than 100 data centers worldwide with more than 715 million global users. However, incidents may happen in cloud systems, which can threat the reliability for cloud systems. In this example, an outage happens in the cloud system can cause $19 billion loss, and only a little bit can be insured. However, such an incidents are inevitable. It can affect the customers from the cloud systems, and the customers can submit tickets to the cloud system to talk about their problems and ask the cloud provider for help. And ticket can, this is an example of the ticket. It has multiple fields like the symptoms describing the tickets, locations, time, and categories. Because of the large scale of cloud systems, there are thousands of services and hundreds of millions of customers in cloud systems, and there are overwhelming tickets that we can receive. So the problem here is that how to identify duplicate tickets in cloud systems so we can reduce the efforts to process the tickets. There are many studies that try to capture the similarity between tickets to find their duplication. In this example, the three tickets are very similar, so such a method can capture their similarity, like using natural language processing techniques like topic modeling based methods, word-to-vector based methods, and BERT based methods. They can capture the similarity between the semantics of these tickets, so they are effective for the tickets. However, duplicate tickets in cloud systems may have very distinct semantics, so these solutions may be ineffective. This is an example in Microsoft Azure. When an incident happens on the disk resource provider service, there are multiple services can be affected, like virtual machine, Kubernetes, and Databricks. So we will receive multiple tickets from these three services, and we can observe a spike in these three services of the tickets number simultaneously. And the following is an example of the tickets that we can receive from these three services. And we can see that their symptoms are very different, and they have very different semantics. So based on the semantics to capture the duplication, it is not very ineffective. So we have very diverse symptoms because the customers using different services can experience very different problems. The reason behind that is the dependency between different services. In this example, the virtual machine service, Kubernetes service, and the Databricks service all depend on the disk resource provider service. So these three services are affected simultaneously. So to overcome this problem, our intuition is to use a two-stage linking strategy to group the duplicate tickets. The first is that we identify the impacted service by the same incident. As shown here, we firstly find VM, Databricks, and Kubernetes are affected by the same incident. Then we find what are the tickets that are related to the incidents of the corresponding service. The key idea is that the key idea is shown as follows. We use the alert that are generated by the services. What is an alert? Alert is generated by monitoring rules, and this is an example of an alert. The monitoring rules describe that if the latency of an API is more than a threshold, the alert will be generated, describing that something is getting slower. And an alert can have time, locations, and the concrete issues and severities and other fields in an alert. So when an incident happens, we will find what services are affected. Then we find what tickets are generated. But alerts can help us to produce more concrete information. So we transform this problem to find what alerts should be linked and what tickets should be linked to the alerts. In doing this, we can find all the duplicate tickets caused by the same incident. So the key idea is to leverage the cloud runtime information, that is the alerts. And in the aforementioned example, we can find A1, A2, A3 are 3 alerts that are linked to the 3 services, as shown here. And for the second step, we will link the tickets to the corresponding alerts that are related. So we firstly link A1, A2, A3. Then we link A1 to T1, T2, A2 to T3, T4, A3 to T5, T6. So T1 to T6 can be grouped together as duplication. To achieve this, there are two challenges. The first is that alerts are massive and noisy. There are indicative alerts that are actually related to the incident, and also regular alerts that are not actually related to the incident. It may only just record several runtime information of the cloud system, like CPU utilizations. And the second challenge is that there are high feature cardinality for both alert and ticket. For example, alerts can have free text and more than 2,000 components and more than 10,000 IDs. And the same is for tickets. So when we consider to combine alerts and tickets, there should be a very large feature combinations to be considered. So we propose IPAC to overcome these two challenges. This is the overall framework of IPAC, and it may seem a little bit complicated, so I will go through it one by one. First, we use alert parsing techniques to reduce redundant alerts. The redundant alerts is triggered by several monitoring rules like this. It can generate redundant alerts as shown here. The numbers actually are increasing due to an incident. So we use log parsing techniques to pass all these alerts to a more compact way, which we call it as an event. And second, we link alert to alert by using incident profiling. It has 2 steps. The first step is an offline step called static event relation learning. We learn the relation between every 2 events. We call that the events here means that the past alerts, so they are actually alerts. So we learn the pairwise PMI values of the events from historical alerts. Then a new incident happens. We input new alerts here to construct a complete event graph. And on this graph, we put the PMI values on the edges. Then we prune on this graph to just leave the indicative alerts here and reduce the regular events. In doing this, we can link alert to alert without considering the irregular events. Next, we link tickets to alert by using a neural network technologies. And we use AIN, which is called Alternative Interaction Network, to link alerts to events. When we want to link them together, we need to consider their feature combinations. Traditionally, we may use one hot to encode these features, so the length of the one hot vector will be very long. So the models will never learn any indicative feature combinations. To overcome this problem, we use decompilation techniques to embed each feature as embeddings. For example, here, embedding 1 and embedding 2. Then, if we want to consider their feature combination, we use an interaction, which is a dot, to represent the feature combination of these two embeddings. After that, we input the interaction to a model to learn their correlations. And more details can be found in this paper. After all this, we can group all the aggregated tickets together, and these tickets can be sent to a support team for batched processing. Then, on-call engineers can also have knowledge about the alerts as well as aggregated tickets, so they can assess the impact of an incident. And we use the 3 research questions to evaluate IPAC. And here we only focus on the first research questions, and we leave the 2 questions in this paper. And we use dataset collected from Microsoft Azure, covering 3 regions and tens of services in Azure. And we use a metric to evaluate how well the duplicate tickets can be grouped together, which is we use precision, recall, and F1 score. And we can see the overall performance of IPAC is higher than all the baseline methods. And we can see that all the baseline methods can achieve a very high precision, but their recall is very low because they just capture the semantic similarities. So they failed to group all the tickets together from different services. And IPAC only sacrifices a little bit precision and achieves the best overall performance. And to conclude, in this paper, we propose that duplicate tickets in cloud systems can have very different semantic content caused by the interdependent services, making existing work ineffective. And we propose IPAC to solve this problem with alert linking and alert to ticket linking. And finally, we evaluate IPAC in the dataset collected from the production environment of Azure, and it achieves the best performance comparing with existing solutions. And this is the end of my presentation, and thanks for your attention, and welcome to some, happy to receive some questions.
Thank you so much to Jinyang. We run a little bit out of time, so maybe there is time just for one question.
Hi. I was wondering, how did you get the labels for the duplicate incidents?
Okay, the labels are actually in Microsoft Azure. We will manually link the ticket to alert. So if one incident happens, we know what alerts are related to that incident. And we also have the tickets linked to the alert. So we actually do the same thing as IPAC did manually to get all the labels. Yeah, thank you.
Great. Let's clap again for the presentation. Thanks so much. Now we go to the second presentation by Sungmin Kang from the Korea Advanced Institute of Science and Technology. The floor is yours.
Okay, good afternoon, everyone. Thank you for coming. I'm Sungmin, and I'm pleased to be able to present our work exploring large language model-based general bug reproduction, done with my co-first author, Juyeon. To start off with the motivation of our work, as you all probably know, users will report bugs to developers. These are called bug reports, and bug reports are important to the extent that many projects have separate systems to handle bug reports. Now, one important activity in report handling is bug reproduction, where a natural language description of the bug will be transformed into a repeatable, ideally test that encases the bug. Now, in our paper, we argue that automatic bug reproduction would help developers significantly. This is because, for one, bug reproducing tests are key to both automatic debugging techniques and manual debugging processes. Furthermore, in our paper, we mined 300 software repositories with test suites and found that a significant proportion of tests actually originate from bug reports. Now, we are not the first to identify that automatic bug reproduction is an important problem, but up to now, only partial solutions have been explored. For example, Zoltani and others proposed EvoCrash, which aims to reproduce crash bugs. However, crash bugs are ultimately only a small proportion of all possible bugs. Meanwhile, Song and Chaparro used natural language processing tools to parse reports into key aspects, but they did not go as far as generating bug reproducing tests. It's worth questioning why these techniques stopped before tackling the more general problem of bug reproduction. We argue that this is because, in its general form, bug reproduction requires strong natural language processing capabilities. Let's take a look at the example bug report on the slide. It says sum equals methods will return true if both arguments are NaN, and that this contradicts the IEEE standard. Here, the expected behavior is implicit, but it's never explicitly spelled out, and so it can be difficult to automatically process this report unless an automatic technique has a strong grasp of natural language. And what has a strong grasp of natural language? Well, large language models have been demonstrating increasingly strong performance on question answering benchmarks involving natural language, such as the GPT-4 model, and they have also been demonstrated of being capable of generating plausible looking code. And as a result, we argue that large language models are key to tackling the general problem of bug reproduction. At the same time, just using large language models has low usability from the perspective of the developer. For example, they are prone to hallucination, as you can see on the left. All the yellow text is false, and from our perspective, we don't want to present the developer with demonstrably false results. As you can see on the right, developers also value having less false positives from automatically generated results. And so when we present any results, we want them to be quality results, and to that end, we add a post-processing pipeline. To summarize up to now, we identified that the general bug reproduction problem has been a challenge due to the difficulty of natural language processing, and to solve this, we proposed Libro, which first uses large language models to generate multiple candidate tests, and subsequently applies post-processing to ensure that the developer will only see the best results. Now, how does Libro actually work? We will first describe how we use large language models. Language models are ultimately autocomplete machines in the sense that they are trying to predict the most likely word or phrase that would follow a certain context. And so from our perspective, what we want to do is identify the context that would maximize the likelihood of a bug reproducing test to follow. We do this by constructing a prompt, as you can see on the screen. We will first provide the report content, which is here in Markdown. Then we will append a special phrase that makes it very likely that a bug reproducing test would follow. You can see that it contains a sentence asking for a bug reproducing test, along with the final tokens, public void test, that indicate that a test would follow. Along with this prompt, we prepend a number of examples highlighted in gray here, as large language models are known to benefit from the provision of a number of examples. Now, we have constructed a prompt from which we can sample multiple candidate tests and candidate tests. We sample multiple tests in the hope that at least one of them will actually reproduce the issue at hand. In our case, we sampled 50 tests by default. But here, we have 50 candidate tests, but simply showing all of them to the developer is infeasible. After all, this slide is already somewhat nauseating, and it's not even real test code. Some of the tests might be invalid as well. For example, they might not even compile. And so before we present these results to the developer, we need to do quality assurance. To do this, we go through 3 steps. Number 1, we will execute the test and cluster them based on these execution features. After that, number 2, we will, based on the clusterization results, we will decide if the results are reliable and ultimately whether to present any results to the developer. Finally, number 3, we will rank the tests in the hope that at least that the developer will see the actual bug reproducing tests first. To execute the test, we need to inject them into existing target files. And to do that, we identify the test files that have the greatest lexical similarity with the generated test and inject the test into those test files. Then we add import statements for any unmet dependencies. And subsequently, Libro will try to execute the tests at which 4 results are possible. Either the test might not compile, or the test might pass in the buggy version, indicating that it's not actually reproducing a bug. This leaves us with the critical failing in buggy, or FIB tests as we call them, which need to be inspected by a developer to check whether they actually reproduce the issue at hand. And so ultimately, our post-processing is aimed at reducing this developer inspection effort. To do this, we will cluster the failing and buggy tests based on their error message. For example, test 29 and test 49 might share the same error message, so they would be grouped into the same cluster. Then we would show results only if the cluster size is if the maximum cluster size is larger than a certain threshold. We do this as the maximum cluster size can be thought of as the confidence that Libro has in its overall output. And therefore, if it is too small, we will discard all of the results and simply not present any results for that developer and not bother the developer. If we decide to present results, on the other hand, then we will rank the tests based on 3 heuristics. First, we will rank them based on whether the test error message includes an exception type that appeared in the bug report. Then we will prioritize tests from larger output clusters. And while not on the slide, we will finally prioritize tests based on their length, prioritize shorter tests to reduce the developer inspection cost. To recap what I've said up to now, we did prompt engineering where we constructed a prompt to maximize the likelihood of sampling a bug reproducing test. Then we queried from the large language model multiple times, and then did post-processing by injecting these tests into existing test files, actually executing the tests, and based on those features, we selected and ranked the tests for developer consumption. Now, how well does Libro actually reproduce bugs then? Well, we evaluate this on 3 fronts. First, efficacy, in terms of how many bugs could be reproduced by Libro. Second, in terms of efficiency, in terms of how many resources are required to achieve this level of performance. Finally, generality, in which we evaluate Libro on a held-out bug dataset that was likely not part of the training data of the large language model that we used. First, in terms of efficacy, we found that around 1/3 of the bugs in the Defect benchmark that we evaluated against could be successfully reproduced by Libro, indicating that a substantial number of bugs can actually be automatically reproduced. Meanwhile, Libro could significantly outperform all of the baselines that we compared against over all of the scenarios that we looked at. In terms of efficiency, we found that Libro could reproduce a single bug in less than 10 minutes on average, indicating that Libro could be applied in a practical setting. Furthermore, our selection algorithm was significantly better than the random baseline, and by controlling the threshold at which we presented results to the developer, we could control the overall precision of Libro. Meanwhile, our ranking performance was also significantly better than the random baseline, as you can see on the bold text in the table. And so combined with the selection and ranking performance combined indicate that our post-processing pipeline could effectively reduce developer inspection cost. Finally, in terms of generality, where we evaluated Libro on a held-out data set, we found that Libro could reproduce around 1/3 of the bugs here as well, which is similar to the RQ1 results. And so we find that Libro could somewhat generalize to other data sets, and the selection and ranking heuristics also showed robust performance on this different data set as well. Those were the quantitative results. Regarding the qualitative results, here, first of all, is a successful example where the bug report says that a certain method cannot handle a negative offset of less than 1 hour. If we look at the test generated by Libro here, indeed, it has generated a test with a negative offset of less than 1 hour, and it is also distinct from the developer-written test in this case. Hence, we can argue that Libro is capable of generating unique bug-reproducing tests. Meanwhile, Libro does not always work, and when failure happened, we found that a large number was due to a need of complex test helper functions that were very project-specific, and in those cases, the large language model did not know that it needed to use these project-specific functions. Other failure causes included low report quality or the large language model misunderstanding the report. In conclusion, we tackled the problem of reproducing general bugs from bug reports. To solve this, we proposed Libro, which combines large language models and post-processing to effectively reproduce bug reports. Our evaluation shows that Libro can successfully reproduce bugs and that its post-processing heuristics work in a robust manner. That's it, and thank you for listening.
Thank you so much, Sungmin. Thank you.
Thanks for your talk. It is very nice work. I have a small question. I just wondering for the test selection and prioritization, whether it can also be conducted by the large language model.
That's a good question. We didn't experiment with that setting, but I think, there are also studies that there's a reason we mostly focused on rule-based tools. This is because there's a study that developers will mostly be persuaded by objective execution measures, and so large language models, while they are great, they are also somewhat unreliable, and so we wanted to use concrete execution results to hopefully persuade developers that these prioritization results were meaningful.
Next question. Yeah.
Thank you for the presentation. And I have a question about whether you investigated the length of the test cases and whether shorter were more successful in reproducing than longer ones, or that doesn't really happen, or if you have any insights on that.
Okay, that's a great question. We didn't actually look at the correlation between length and success of bug reproduction, but we did have some examples where actually a substantial portion of failures were due to the large language model synthesis limit, where we set the synthesis length to 256 tokens, and the large language model simply couldn't complete the bug reproducing test in time. And so I would suspect that there is a weak negative correlation between the length and the actual reproduction success rate, but we would need to actually inspect that, yeah.
Great.
Okay, so thanks for the presentation. So my question is, how many examples do you give in the future learning? And the second question is the example you give is consistent across all the tasks? Yeah.
Okay, those are also great questions. First of all, we provided 2 examples maximum. We experimented with different example numbers, and as you can see, no example reproduced 1, 2. Oh, okay, you can't see anything. But providing more examples helped performance up to 2 examples. We're currently experimenting with more examples, but at the time, we had a prompt limit issue, and so we didn't add a lot of examples. So 2 was the limit. Regarding the consistency of the examples, we found that 2 manually curated examples that we identified showed the best performance and were actually better than using examples from the source project itself. So that was a bit surprising. We couldn't exactly identify why, but one of the reasons we suspected was when the example was from the same project, the large language model had a tendency to simply copy the example test, and those were, of course, not the actual answers, so it would consistently get them wrong. So that was one thing that we suspected why just using the same examples for everything worked better.
Great. Now we have time for one very quick question. Yeah.
Thanks for the talk. So I'm just wondering, because the bug report is usually written by the users or developers, so sometimes it can be some missing steps in the bug report. So whether the large language model can somehow predict it, or try to have some potential value to solve it.
Yeah, I think that large language models are good at that kind of they're capable of that kind of logical infilling. And so as in the starting example that I had with where the expected behavior was only implied, the large language model actually successfully reproduced that bug. And so as long as the intermediate logic is not too complex, I think it can kind of impute the intermediate steps in certain cases. So there is some promise in that direction as well.
And another round of applause for Sungmin. Thank you so much.
Thank you.
And in the meantime, I'm asking Hao Nanzu to come up and prepare his presentation on the reproducibility of software defect datasets.
Okay, so we answered 2 questions in this study. The first, what is the reproducibility of software defect datasets and how to fix reproducibility issues on those software defect datasets? So what is reproducibility? In software engineering, reproducibility means the same result should be repeated as long as we repeat the same procedure of the software process. And for software defect artifacts, they are artifacts for bugs. So reproducibility means the buggy version of the code, if we run the build script on that, the bug should exist. And for the fixed version of code, if we still run the build script, there should be no bugs on that. If there's no reproducibility on those software defect datasets, we'll have misleading conclusions from the studies using these software defect datasets, and we'll have some reproducible studies, and we'll have inability to perform future studies. So this could be very problematic to software engineering community. So we want to know what does reproducibility means to each software dataset, and what's the reproducibility of those ones. We select a set of software defect datasets which are popular, and those are defect datasets for Java artifacts with whole project incidental code snips, and therefore functional bugs instead of performance bugs or something. So we have Defect4j, growing bugs, bugs.jar, and BS. And the first thing is we found that reproducibility actually means differently to each dataset. For this, we iterate the dataset documentation, publications, and the dataset infrastructure code. And we found that there are actually four criteria for each dataset, which is existence, number match, name match, and status match. Existence means artifacts is defined as reproducible as long as there is a bug in the buggy version and we can reproduce. And all datasets will check the existence bug, but only bugs.jar and beers, they will only check existence and they say the artifact is reproducible. And number match means it's based on the existence, but the number of the failing test should match the original reference. And Defect4j, growing bugs, and bugs1, they will check if the number match the original. And for name match, it's based on number match, but the number of names, they should both match the original reference. This is also for Defect4j, growing bugs, and bugs.jar. Oh, sorry, bugs1. And status match is most strict one. That's only for bugs1. In status match, artifact is only reproducible only if number, name, or failing test, and CI/CD build status match the original reference. And we want to know the reproducibility of those ones. In our experiment, for each dataset, for each artifact, we check out the source code, we run build script, we run tests. And we got some test logs, we find the test failures compared with the original reference, and we determine it's reproducible or not. When we are determining it's reproducible or not, remember that we have different criteria to different datasets, but in this study, we apply all criteria to each dataset. For those default ones, they are highlighted. And for example, the Defect4j, which is a manually created software defect dataset, it uses name match as criteria, and its reproducibility is 96%. This is actually good, but for all other datasets, those ones are automatically constructed. The datasets is ranging from 26 to 69%. For example, the growing bugs only have 29%, bugs.jar 26%, bugs1 69%, and bears 54%. So this could be very problematic if those software defect artifacts are not reproducible. So we want to know why they are not reproducible, and we want to know if there's any approach we can fix the reproducibility of those software defect datasets. So this brings us to a case study on bugs1 for the reproducibility. bugs1 is automatically constructed software defect datasets with 1795 non-flaky Java artifacts at the time of our study. On bugs1, we have 3 research questions. First one is the frequency of the breakages, and the second one is root causes and fixes for software breakages. And the third one is how can we prevent software breakages. For bugs1, we conduct reproducibility tests on average every 11 days, and we have 36 test results in 13 months period. And for the criterion, we use the most strict one, which is status match, which is also the default for bugs1. So for the frequency, we found that software defect artifacts break very frequently. In total, we have 1124 out of 1795 artifacts broke at least once, and 275 artifacts broke multiple times. Take a look on the figure here. There we we have 36 test suites. And for example, test suite 11 and test suite 12, it's only 11 days in between, and we have 4 nearly reproducible and 69 nearly broken artifacts. This is just 11 days. So, which means it's really hard to maintain a data set with high reproducibility because the artifacts, they broke very frequently. So we want to know what's the root causes and if there's any fixes for those software breakages. We identified 1606 individual instances of breakages, and we manually identified 11 root causes and manually implemented 10 patches to patch 10 of them. For example, the first one, Maven TLS failure here, that caused software-defined artifact to break because at some point, the Maven Central, they just disabled all connections using TLS 1.0, and the fix is straightforward, just to update TLS to 1.2. And one insight is that most of the patches are related to the system or project dependencies, and more importantly, almost 1/2 of them are related to project dependencies. For example, the Maven TLS failure in skill link, unavailable Gradle plugin, and the deprecated check style links. So this really motivates us to take one more step to do breakthrough prevention to ensure long-term reproducibility. For this, we propose dependency caching and artifact isolation. Dependency caching is to utilize the offline mode of the build system to cache all the dependencies to the software-defined artifact. So when we are reproducing the build process, we don't need to download anything because all the needed dependencies are in the local directory already. Initially, we have 1,700 artifacts successfully cached, and for artifact isolation, it is based on the assumption that those cached artifacts should be reproducible even without the internet connection, but that's not always the case. We need to fix something like disable the Travis caching uploading functionality or something. So finally, we have 1,257 artifacts successfully isolated. For evaluate dependency caching and artifact isolation, we use 20 extra test suites in another 8 months period. And for the cached artifacts, the reproducibility is among 81% to 85%. And for the isolated artifacts, the reproducibility never went down to 95%. This is actually incredible because remember that Defect 4J, which is the best software-defined datasets in terms of reproducibility, its reproducibility is 96%, but it's manually created software-defined datasets. They made like 800 software-defined artifacts in 10 years. But in the isolated box one dataset, the reproducibility is over 95%, and it is automatically constructed, and it is still growing to a larger scale. So, lessons learned. All software-defined datasets suffer from software breakages, especially for those automatically constructed ones. And most of the software breakages are related to kind of dependency issues. And dependency caching and artifact isolation can effectively prevent software breakage and ensure long-term reproducibility. And for now, we are monitoring the real-time reproducibility of the box one. The latest data is 98%, just yesterday. That's it, thanks.
Thank you so much. Thank you so much. Are there any questions? One question here.
Thank you for your talk. I've had the chance to be involved in a benchmark project in C that had plenty of breakage. And I'm curious about the recommendation you made at the end involving dependency isolation. One of the things we struggled with was a tension between heavyweight approaches, like having a full virtual machine setup where we better guarantee reproducibility, and using something lighter and more popular like Docker, but that might not do the dependency isolation correctly and might lead to more breakage. Since you've been studying this more extensively, do you have any recommendations for a sweet spot between those, or how vulnerability benchmark set creators should ensure the isolation of dependencies?
Here is the thing. For the box one, it uses Docker containers to ensure the reproducibility because all the dependencies are in the Docker container. But Docker container is not the only solution. Like for Defect 4j, it's a good one, right? It does not use Docker containers because when setting up the Defect 4j, it will download all the dependencies in the code repository. But that's only practice for Defect 4j. No other datasets are doing that. So my recommendation is we need to care about reproducibility, and we need to do something on the reproducibility. And it really depends on what you want to choose the approach to ensure reproducibility. Like if you don't mind use Docker containers because it will cost more space, disk space. You need to do something like Defect 4j to download all the dependencies for all artifacts. Thanks, good question.
Thanks so much. Any other question? No? But maybe I have one. So how do the strategies currently employed by dataset maintainers fall short in ensuring the reproducibility of software defect artifacts?
Can you repeat that?
How do the strategies currently employed by the maintainers fall short in ensuring the reproducibility of software defect artifacts?
In this study, we just proposed the issue of the reproducibility that was ignored for a long time. And we proposed the dependency caching and artifact isolation, which is definitely work on this scenario. But artifact isolation is used when we are disconnecting the internet to say like our artifact is reproducible even without internet connection. But this is not all the case, because this case we are talking about software defect artifacts. They don't need internet access actually. But for other services, we need to really consider something related to dependency, like to ping the dependency version, or to ensure that dependencies are already always reachable in the future building process.
Yeah, and maybe also related to that, are there particular strategies that are more effective than others in preserving reproducibility?
Oh, you mean dependency caching and artifact isolation in between? Actually, the artifact isolation is based on the dependency caching, so it's like a trade-off. Artifact isolation will definitely brings the reproducibility much higher, but you need to to do a lot of work to make sure it's reproducible without internet connection. So it's really based on what's your situation, what's your scenario.
Yeah. Well, I would say thank you so much to Haonan for his presentation, and I would like now to ask Junjie Wang from the Chinese Academy of Science to come and to prepare her presentation about context-aware bug reproduction for mobile apps.
Hello, everyone. Thanks for coming. I'm Junjie Wang from Chinese Academy of Science, Institute of Software. Our work is also about bug reproduction, and it is especially for mobile apps. As mentioned by the second speaker, the online issue tracking systems such as GitHub, Bugzilla allow the developers and users to report various bugs. And these bug reports are becoming a non-neglectable source of information for improving app quality and user satisfaction. And in the bug report, the submitters will describe the process they used to trigger the bug. Usually in the form of text, as shown here, it is the reproduce steps. after receiving a bug report, the developers usually need to reproduce the bug in order to effectively debug it. That is, they should to execute these operations in the app and to check whether the crash is truly occurred. However, the bug reproduction is usually time and effort consuming since it involves the natural language comprehension, the app usage acquisition, and human app interaction. So it is highly demanded for an automatic approach for the bug reproduction. And existing techniques for the automatic bug reproduction would typically utilize the natural language processing techniques to understand the reproduce steps based on the syntactic analysis and heuristic rules. This is to map the reproduce steps with the GUI component, and then they would conduct the path planning, usually in a grid-based exploration. And here is the example. They would extract the target information username with the syntactic analysis, and this will be matched with the displayed text of the GUI component. However, when we try to reproduce the real-world bugs with these existing techniques, we found there are several challenges to handle it from successful reproduce. The first challenge is that the reproduce steps in natural language is usually improvised or incomplete. This might make the syntactic analysis incorrect, thus hinder the successful matching with the GUI component. And the second challenge is that the name-related information of the GUI component may be missing. The existing techniques would work good in the text-like GUI component, like the examples in the left side, but they might fail in the icon-like component, like the examples on the right side. And the third challenge is that the reported reproduce steps may be incomplete, and some obvious steps might be omitted by the submitters. For example, the submitter will only say they perform the login operation, and they would not mention they have entered the username and entered the password. The fourth challenge is that there might be similar GUI component in different GUI pages. For example, there is text input of username in both the register and the login page. So the bug reproduction is like walking in a maze, and existing grid-based exploration may be confused by the similar GUI component in different pages, and they might stuck in a local place. And so to address these challenges, we produce Scope Droid, which is a context-aware bug reproduction approach, which can reproduce the crash from a text description of mobile bug reports. And like existing studies in mobile app bug reproduction, we only focus on the crash because it is observable. However, the whole technique can also work in other types of bug reports. And our work has 3 main steps. Firstly, we will construct an initial state transition graph, STG, and extract the necessary information about the text and the icon. Then, secondly, with the extracted information, we will build a multimodal neural network to predict the possibility of each GUI component to each reproduce step, and will outcome a fuzzy matching matrix. This step can help address the first 2 challenges. And thirdly, with the fuzzy matching matrix and the initial STG, we will conduct the path planning from a global perspective, and also enrich the STG and interactively perform the path planning. This will help address the last 2 challenges. I will say more about each step. The first step is STG construction and information extraction. We conduct the initial STG with a random exploration tool, Droidbot. It then extracts the information from its layout file, including the text information like the display text, the context information like the neighbor text. Also, we extract the icon image. Then is the second step, fuzzy reproduce step matching. We build a multimodal neural network for matching the reproduce steps with the GUI component, and it derives a fuzzy matching matrix. For the matching network, we use the ResNet encoder to help understand the icon image. And we also utilize the cross encoder, which is implemented as a DistilBERT to help understand the textual information of GUI component and the reproduce steps. Compared with existing approaches, our work can help better utilize different sources of information and better capture the semantics. Also, we can mitigate the disturbance from incorrect semantic analysis. As we all know, training a neural network usually requires a large amount of training data, and human labeling the data is always effort-consuming. So we develop a heuristic-based generation method for training the neural network. Generally speaking, for GUI page and its GUI component, we will extract the information. And with heuristic rules, we can generate the reproduce steps associated with the GUI component, and this will automatically serve as the training data. And for the third step, the path planning and SDG enrichment, we design a weighting algorithm which will determine which candidate path is most likely to trigger the crash. It takes consideration about the matching degree as well as the exploration path to avoid meaningless loop and to what degree the reproduce path is covered. Also, compared with existing studies, it has advantage about it can better distinguish similar GUI component, and its planning is from a global perspective, so it can mitigate the problem of missing steps. We evaluate the approach from 4 perspectives. Firstly, we evaluate its effectiveness and efficiency. The results show that our approach can successfully reproduce more crash reports than the baselines, and it also requires less reproduce time. And secondly, we evaluate the matching accuracy of the neural matching network. Results also show that it has a relatively high accuracy, which lays a solid foundation for the follow-up path planning. And the third research question, we conduct a user study to let the users to evaluate its usefulness. And the results show that the practitioners think it is between useful to very useful with this tool in bug reproduction. And fourthly, we evaluate its robustness with the mutated reports. That is, it is semantic similar, but it is described in a different form. And the results also show that it can still achieve high efficiency. Then I will conclude our work. Firstly, we propose a novel approach to automatically reproduce the bugs from mobile apps directly from the textual described bug reports. And secondly, we conducted experimental evaluation with promising results. And thirdly, I also want to mention our matching method, which can match the natural language description with GUI event without manually labeling training data. It can also potentially motivate and facilitate other tasks such as user interface operation and task screenshot generation for visual assistance. But also I think, as the second speaker mentioned, with the development of large language models, I think this whole technique can also be further improved. Thank you.
Thank you so much to Pinjia. First question.
Hi, thank you for your presentation. And I have a couple of questions. One, whether the exploration algorithm consider backtracking. So when you select an element to be clicked, might be the best provided by the network, but not the right one. So do we have any ways to go back and maybe try a different button?
Yes, actually, I think we can think different aspects as mentioned maybe in this slide. We think three aspects, whether it is matched with the reproduce step and whether this exploration path has already long enough since it might include some meaningless loop. And we also consider to what extent the whole reproduce path is are covered. So I think it comes not the most, maybe not the most suitable one, but it is planning from a global perspective. And if we see it could not trigger the issue, we might return to maybe our former status and replanning it.
And the follow-up question, which is very related, it's in this way, are you able to handle also like steps to reproduce, which lead to multiple actions in the GUI? For example, if I write send an email, this might be clicking on a button, entering some text, and clicking send, right? Is it a similar way in which you handle this situation?
Actually, in this data set, actually we can only reproduce about 63% of the crash report, and there are a large percent of bug reports we cannot replay. And one of the main issues is just as you mentioned. For example, they only say they perform the login, but they did not mention they have entered the username and the password. And for this situation, I think this current approach cannot reproduce. Maybe we can incorporate some common knowledge and to help this situation can be addressed.
Great, thank you, and it's good for future work, right?
Yeah, thank you. Thank you for your question.
Thank you so much. Another question? Yeah, please.
If we go back to your recording slide where you're recording the bug, I've got sort of two questions. One, I hope I won't be a bit cross with me about, but the first one is, have you considered using a restricted natural language to do the recording to make it easier to analyse that for the on the input side, and also easier for humans to see similarities? So at the moment you're using open natural language, is that right? When you're recording the bugs.
Yes, I think this work only tackles the situation about the natural language described reproduce steps. Maybe there are also other kinds of steps in video or something else, but this work is only focused on the natural language described one.
Good. If there are no further questions, I would move to the next presenter, Xidong Feng from Monash University. And sorry, and thank you so much for for your presentation and the answers. Xidong will present us Read It, Don't Watch It, Captioning Bad Recordings Automatically. The floor is yours.
So, hello everyone. My name is Xidong, a PhD student from Monash University. Today I want to introduce our paper, Read It, Don't Watch It, Captioning Bug Recordings Automatically. So first, I want to have a background of our paper. So what is the bug recording? So bug reports are virtual for software maintenance that allow users to inform developers of the problems encountered while using software. However, writing a good bug report can be really difficult. Therefore, many users attempt to use the bug recording significantly lower the bar for documenting the bug report. It is easy to record the screen, and it has more detail and context for developers. Unfortunately, in many cases, watching the bug recordings and understanding the user behaviors can be time-consuming and tedious for developers. So this is because, first, the recording may play too fast to watch, so the developers have to watch the recording over and over again. And also, some recording can be blurred or in a poor quality that make developers hard to read. And lastly, some users attempt to use the visual indicator to indicate their user behaviors on the screen. However, we find that the user indicator is too small to be realized. So inspired by that, we find that in the movie industry, they always use captions or subtitles to add clarity of details, better engage users, maintain concentration for longer periods, and translate the different languages. So taking this sense, we propose an approach that's given an input bug recording and propose an automated approach Capdroid to generate nature language descriptions as subtitles. So to start with the approach, we conduct a preliminary study of bug recordings to understand the user behaviors from the end users to motivate our approach design. So we randomly collect 5,000 bug reports from the Google apps, and we randomly select 1,000 GUI recordings as the experiment dataset. During our manual labeling, we classify 3 types of the touch indicators. So first is the default one that is usually embedded in the mobile system. And some users attempt to record their screen using the emulators. So they will use the cursor as the touch indicator. And lastly, some users attempt to use the third-party recorders, which normally have some custom touch indicators. With it, and we start with our approach. So the first phase is to segment the recording into a sequence of action clips. So inspired by the signal processing, we adopt an image similarity matrix called SSIM to compute the similarity sequence of consecutive frames. And we find that there's some patterns in this similarity sequence, and so we adopt a pattern matching to classify these actions. For example, for the tap action, it usually have dramatic drops, and for the scroll action, it has some continuous motion, and for the input action, it is similar to the tap action, so that we also use a keyboard detection method to detect whether there is any keyboard in the frame. Next, we attempt to infer the attributes of the action for each clip. So to achieve this, we adopt tailored methods for each action. So first, we want to infer the tap location. To achieve that, we use the deep learning method since there are diverse types of the touch indicator in the recording. And for the scroll action, we use the template matching to infer the scroll offset and the direction. To infer the input text, we use the text difference between the frame that's launched the keyboard and the frame that's end the keyboard. Next, after we obtain all of this information, we can then generate the natural language description. So, however, since the GUI recording does not have any meta information such as the hierarchy or some elements inside, so we adopt a non-intrusive method to understand the GUI. So these methods are usually widely investigated in the previous studies, and we use the element detection, icon captioning, absolute positioning, and the element relationship. So of the information that we have obtained, we can then generate some templates to create the subtitle and embed it in the recording. So to evaluate our approach, we arise the first research question is how accurate is our approach in segmenting action clips from recordings? So we set up 5 baselines and we find that our approach is much better than that of other baseline in all metrics, including video segmentation, F1 score, and accuracy. So we raised the second research question on how accurate is our approach in inferring action attributes from clips. So we set up 2 state-of-the-art baseline, and we find that our approach outperforms in all actions for tab, scroll, import action, respectively. And lastly, to assess the usefulness of our approach, we conduct experiments on how useful is our description for replaying bug recordings. So to answer this, we conduct a user study with few developers and ask them to replay the bug recordings with our generated description, and also ask the experiment group, and we have another control group that's replay the bug recordings with the step description written by the users in the GitHub. So we find that developers reproduce the bug recording much faster with our descriptions, and they also admit that our approach can provide clear and concise step descriptions. So in summary, I think we are the first one that's using some video captioning techniques to the software engineering domain, and we propose CapDroid to non-intrusively segment recordings into clips, infer the fine-grained user actions, and create action descriptions as subtitles to support developers in reproducing bugs. We also have comprehensive experiments, including the automated experiments and a user study to demonstrate the accuracy and usefulness of our approach. And we have released our source code in GitHub and put our paper in the archive. And feel free to have a read and try our code to provide any feedback. Yep, thank you.
Thank you so much to Jinyang, who actually finished 2 minutes earlier, so we have now a little bit more time for questions.
Thank you for your talk. I think it is a great work. And I have a question. So for your work, you generate the caption for the actions for testing, right? So I think in some stages, we might use that captions as a test script and use the generated test script to help developers to only use that textual test script and not use the recorded video for reproducing the bugs. And what difficulties do you think there exist for such textual test script generation? Like, I think for one difficulty I think of, like I just heard the third speaker's work, and there might be some steps that the users might not record into their videos that we might need that for a complete test script. And there might exist other difficulties, and I want to know if there are any insights from you. Thank you.
Okay. Thanks for the question. Yeah, for the natural language description to the test script, I think like from my experience, it's usually have some missing steps, and usually the natural language description that's written by the user is like inconcise, and they're always using some ambiguous descriptions. Like for example, like for the more options button. So some users may just describe it as a 3 dot, which is really hard to ask the machine to know that it's just a more options button. Yeah, and that's why we use the recording, which somehow can address this kind of information like visually. Yeah, I hope that help address your question.
Yes, maybe a follow-up question. So do you think the difficulties here the same as the third speaker's work? Like if we generate the test grid from the videos, that may be a more easier way because the users might record each step concisely as shown on the video. So maybe it is a more concise way, a more concise way than the just textual steps written by users.
Thanks for the question. I think, so one of the challenges is to ask the users to really use the recording, because some of the users are not happy with it because they usually have some old phone which cannot support the recording system, the recording app. So they might prefer just using some natural language description, which will be easier to describe it. So one of the challenges probably is oriented by the users.
Oh, I see. Thank you.
Thank you so much. We have one question here and here.
Thank you for the talk. I was just wondering in your evaluation, did you observe videos that were more challenging to generate captions for than others, and what type of problem did you observe? Because that's very important to know as venues for future work.
I agree, because the recording, like the description generated from the recording might not be that accurate, because the recording does not have any information in it, like does not have any meta information. So we use some mature methods to generate some understanding from for the UI, but it cannot be 100% accurate. So we use some confidence value threshold to hold it. So for some element that we cannot detect with, we probably use some nearby information, like some elements near or left to or right to describe such information, and which probably makes the description better.
Thank you.
Yeah, thanks.
Yeah, and we have a last question over there.
Hello, I'm Gerard from Belarusian. As a Android developer myself, usually half of the time, we use custom view, which means a text can be a button can be just a text view. So my question is, since your work was based on the image-based, right? My question is, will it recognize if, for example, if a text field was used as a button, will your approach recognize it as a button or a text field?
Yeah, thanks for the question. We use the OCR to detect the text in the UI, and for some icon button which does not have the text view, we will use some icon captioning or image captioning things to recognize it.
What if what if the button looks like a text field? So
what do you mean, like a button looks like a does it have any text?
Imagine just a text, maybe like a help, that doesn't have a hover effect, but it can click and redirect into the other page. Will that be considered as a button or a text field?
Yeah, actually it depends on the mature methods it used, and we set up confidence values on it, because sometimes it cannot accurately detect this information correctly. So if it cannot reach our threshold, we probably use other information like some button, like a reliably button that we recognized, and we use that kind of information to help address the information with low confidence. Thank you.
Thank you so much. Another round of applause for Shilin for his presentation. Thank you. And our last speaker today is Oscar Chaparro from College of William and Mary, and he will provide a demo demonstration about BERT, a chatbot for interactive bug reporting.
All right. Hello, everybody. My name is Oscar Chaparro, assistant professor at the College of William & Mary. Today, I'm happy to be here and give you a summary of our tool named BERT, a chatbot for interactive bug reporting. So as we all know, bug reports are super important for bug management tasks, such as bug prioritization, assignment, all the way to localization and fixing, right? Bug reports are typically textual descriptions of problems that people find in software systems, and they are supposed to contain, at minimum, the observed behavior of the system, OB, the expected behavior, EB, and the steps to reproduce the bug, S2R. These are the main elements for developers. Unfortunately, in many cases, the bug descriptions are poorly written, they are unclear, they provide missing information, and they're hard to understand. And this is one example of a very bad bug report from the Eclipse project in which the user doesn't describe at all what's happening with the system, right? And then the developer is asking for more information about it, including the steps to reproduce the bug. So, of course, low-quality bug reports have an important repercussions for developers and during the bug triage process. And one of the main reasons why bug reports are low quality is basically issue trackers or bug reporting systems, which are merely forms that collect information without any quality verification of the content users provide. Specifically, they have limited guidance on what specific information and how this information should be reported in bug reports. And they give no feedback at all on whether the information is correct and complete. So current bug reporting systems are static systems that and providing quality information in bug reports rests mainly on users. So to address these limitations, we developed a tool called BERT, which is a chatbot that aims to facilitate bug reporting using interactivity. So BERT currently is tailored to mobile applications, and it implements a standard chatbot interface along with different panels that allow that with the goal of guiding the user into reporting better the problems using textual and graphical information. So BERT provides three main features. The first one is guidance. So BERT is able to guide the user toward reporting essential elements of bug reports, the observed behavior, then the expected behavior, and each one of the steps to reproduce the bug. Second, BERT checks the quality of every piece of information the user provides, and it's able to detect missing information, missing inputs, ambiguous descriptions, and it explains these problems to the user, and it asks him or her to fix the problems and provide more information. Third, BERT is able to provide graphical suggestions in the form of screenshots. So for each piece of information that the user provides, BERT can suggest related screenshots of the OB, EB, or S2R, and also it can provide or suggest the next steps to reproduce that the user may have performed for reproducing the bug. I don't have time to give details on how BERT works, but you can find them in our FSC paper, actually. But BERT provides different modules and different techniques that work together to offer functionality, including predefined dialogues, natural language parsing, automated app exploration, graph-based UI modeling, text matching, graph-based step prediction. We conducted an evaluation of our tool using an experiment, and we aim to assess how easy to use BERT is, the usefulness of our tool, and also the quality of the reports collected with BERT. So for that, we used 12 bugs of different kinds from 6 Android applications. We asked a group of reporters to report these bugs using BERT, and also we recruited an additional group of people to report the same bugs with a traditional issue tracker, such as GitHub issues, for example. And we found that the participants indicating that the screen suggestions by BERT are useful in most of the cases. BERT is able to correctly verify the main elements people provide, and BERT is easy to use overall. We also found that the BERT bug reports collect fewer incorrect and missing steps than bug reports collected with the traditional issue tracker, while having similar performance in terms of incorrect expected behavior and a little bit of compromise there for observed behavior as well. BERT is open source. It's an available tool that can be found online, and you can adapt for your systems and mobile applications. And with this, I finish my talk. Thank you very much. And I'm going to leave this video showing how BERT works. Thank you.
Thank you so much to Oscar. Any questions for Oscar? Yeah.
Thanks for the presentation. The first question, I got two small questions. The first one is it's very interesting to have chatbots. So now we got ChatGPT. Can we use ChatGPT for that purpose? And the second one is I find sometimes developers are lazy. Ask them to interact with the robot just to write the bug report. Do they really like that?
All right, first question about ChatGPT. And yes, it's a tool available, and actually in our lab we are exploring how to use ChatGPT for improving bug reporting for sure. And the main advantage of ChatGPT is that it can understand very well what the user is saying. So there is an opportunity there. Second question about the effort, I guess. Maybe you hint that there is an effort by the tool, right? That gives, basically the user will have a little bit more effort, but which is, it's a compromise. We try to design a dialogue that is, that minimizes the effort while collecting information, high quality information in the bug report. So it's a compromise. And overall, according to evaluation, we found that our chatbot is easy to use. There are things to improve for sure, but it's something that we need to work on in the future. Thank you.
Yep. Thank you.
Thank you so much. And if we don't have any other questions, I would like to thank once again Oscar for his presentation. And I hope that you're enjoying this coffee break. And thank you so much for our people at Form Media Lab and our student volunteer for helping us out. Thank you.